So if you hadn't figured it out at this point, the solar nebula theory explains or describes the formation of the solar system. All right. To me, it's much more important what it implies. All right. Yes, it's important to understand how everything came together. And this, by the way, works for any star that has advanced, if you would, elements around it. Okay. This is why they find it really hard to believe that we're not the only solar system out there, so on and so forth. This is where all that comes from, because any star should form in this manner from a nebula. And at this point in time, it's presumed fairly safely that the majority of the nebula out there have way high variety of elements in them. Okay, stars, as far as we can tell, is still just hydrogen and helium. So all that other riffraff has to go somewhere in this process. So that's why they say when they're looking for Earth-like planets, it's a given that there's solar systems, stellar systems, whatever you want to call it, on a whole bunch of these stars. Okay, so that's important to know. But for our case, our purpose, again, remember we started off by talking about the age of the Earth. All right. The idea that everything in the solar system is approximately the same age, which is what I started this conversation with a while back. Now, does that process sound like it's instantaneous? There's no magic wand being waved here. Poof, you are a star with a system of planets going around it. No, there's a hunk of time, a potentially huge chunk of time for that to be taking place. But it can be said within that time frame that everything is essentially about the same age. That's the way we're saying that. And again, in the scope of 4.5 billion years, if it took 10,000 years for this to come together, does that really change your opinion of things? I would hope not. A couple 100,000, yeah, all right. Now we're getting, we could argue about that. A couple 100 million, okay. Now we're talking about decimal points. So it's kind of like you're out with your buddies and you know you had like $5 left somewhere in your wallet or your purse, your pockets or whatever, and you pull it all out and you only had like $4, and you're like seriously bummed because it's $1 and you needed that to buy whatever. Or if you had $10,000 in your wallet and you're like, where the hell did that dollar go? Totally different, right? I would assume. At least for me it would be. I'm not very good with money though, so maybe it's just me. But you get the idea of relevance and scope, okay? We're not going to quibble about the time that it took these guys to come together. What's important is that, relatively speaking, Venus, which is to one side of us, closer to the sun, and Mars, which is to the other side of us, farther away from the sun, are essentially the same age as the Earth. So we could look at Venus and we could look at Mars, and then when we look at ourselves and say, holy crap, these are three sisters that are seriously different for being, for all intents and purposes, twins. Triplets, sorry. So we say, okay, well, this one grew up closer to the sun. This one grew up a little farther away from the sun. This one's the same age as, or same size as us. So that's not a variable. This one's smaller, so that's important. So we could start looking at these other details and try and figure out basically where we are headed. That's the whole point of this, is for the folks in charge to be able to, sort of predict things, make some statements, make some studies, or do some studies. And the more variables you could get rid of, the more easier it is to do and the more ideally accurate your answer is in the end. So really neat stuff. If you can't tell, this is kind of the stuff I dig in geology, and it's neat stuff. Any questions about solar nebula theory? Any of its implications? I use the word meteorite and asteroid a lot. They're kind of interchangeable, but not entirely. Again, for all intents and purposes, they're pretty close. Yeah.
There's elements that we haven't discovered or like classified yet formed from other stars?
Oh, definitely. Let's use the word extrasolar elements. Sure. I think there's definitely probably stuff that other stars have that we don't yet. In our area, there might be some stuff at the end. And there's stuff that they've predicted that they haven't found yet. That's what's weird about the periodic table, and something I'll admittedly don't entirely understand. If you follow its inner working skeletal structure kind of thing, it's not just adding protons. There's more to it. And that predicted certain elements should exist, and they went looking for them and were able to find them, or at least synthesize. I may be using the word incorrectly there, but at least synthesize them, prove that they do exist. There's some way at the end. It's the stuff way at the end that's really skittery stuff that's only visible in a test tube if you heat it to this degree for a fraction of a second. We could glimpse a picture of it, kind of thing. And Californium or Einsteinium, again, one of those way at the end. So is there stuff past that? More than likely. But yeah, I mean, I don't see any reason why going out to other stars that have gone through more cycles than us. We're third or fourth generation star. So if you go out, just a couple generations past us, fusion should definitely keep going. Unless there's some limit that I don't know about or they don't know about yet. But yeah, definitely. Cool question. What else? Okay. So the RCB, almost to scale, right? Who knows? See poor little Pluto way out there. You see why she got demoted. I think Pluto's a boy. Well, at least the god is. But, and the dog is too, I think. So what do we got? Who wants to test their 8th and 5th and 3rd grade knowledge here? Anybody remember that silly mnemonic?
I'll tell you what Saturn is.
What? Well, all right. Well, you wait till they update these things because they're finding rings on all the damn planets now out there. Yeah, and that'll be
right now.
Yeah. All right. So what's closest to the sun? Mercury. Yep, Mercury. Then Venus. Then us. Mars. Jupiter. And I'll be honest, I always forget who comes next, Jupiter or Saturn myself. So Jupiter, Saturn, Neptune, Uranus, or Uranus, Neptune. I forget. And then last but not least, Pluto. And interspersed among there are some dwarf planets, some closer than others. I want to say a lot of them are out in the outer boundaries. Stuff kind of just sucked in. But there are some closer ones in the asteroid belt as well. Ceres, C-E-R-E-S comes to mind. And there's some really just bizarre ones. Now that we're finding these, accepting them as a classification, everyone's out there looking for giant asteroids and hoping they could call it a dwarf planet. But, cool. Okay, so this is narrative. Don't really write it down, and we've talked about most of it anyhow, but it's heavy on the narrative here. So about 4.5 billion years ago, the material that Earth was made of coalesced in space, came together. The process term we used was accretion. This material was elements from the periodic table, okay, obviously. And more importantly, and this is something that we haven't mentioned yet, what we had first and foremost, remember the friction, remember the heat energy we talked about with the sun. What we had was this giant flaming ball of lava hanging in the sky. And again, I think that would go for not just the Earth, but any of these terrestrial planets, the inner planets. Okay, you just have this flaming ball of magma or lava. You'll see a picture in a second here. It's held together by gravity. Okay, And as it is no longer flaming outside, let me check. Yeah, no, we got grass and blacktop and dirt. Apparently, at some point it cooled off. All right. So we've got a long way to go from talking about it cooling off to even where we are now. But to get to it cooling off, we'll hit there next. So this actually came out of somebody's master's thesis, I think. I used to have a quote, like a cite on it. I don't know where the citation went. We got blacked out or something. Looks like something out of a sci-fi movie, but it also looks, if you've ever seen a picture of a cooling lava flow, it looks exactly like that, and it should. The dark gray areas are the parts where cooling has begun, and the yellowish reddish areas are obviously the part that it's still quite hot. And this thing is hanging out there in space, and we'll talk about whether or not it had an atmosphere, but for all intents and purposes it's just out there in the cool void of space. Okay, it's gonna, given the opportunity, once things settle down, once things stop smashing into it, it's going to cool off, start to harden, form a crust, right? Again, we know that's where we are now, so if this happened at some point between now and then, that had to happen. Biggest vocabulary word of the semester. Bless you. Not the hardest word, but definitely the most letters. How do we pronounce that first word? Homogeneous. Anybody else? All right, you guys are good. We always get the homogeneous. Homogeneous accretion theory. No, it's homogeneous. And I don't know, you don't get a whole lot of opportunity to pronounce this word, but every so often, it's homogeneous. What does the word homo as a prefix mean? Same, similar. All right? And what the homogeneous accretion theory is telling us is that on day one, if you would, the Earth was uniform throughout. It was just that flaming ball of goo. Even if that uniformity is because it's a mixed up, muddled mess, it is. And why this is important is, again, that you're going to find, to interrupt myself here, but you're going to find as we go through the semester, there's a handful of what I call the, well, duh moments, okay? And you'll see this in all of science, where you're going to give this, and you should be happy, really. Everyone always grumbles about these hugely complex theories and whatever that they want you to remember. And then we give you this really stupid one that's so obvious, and you're like, well, you know, you make fun of it. Well, be happy. You have an easy one. So here's the problem is that, do we have a homogeneous Earth now? Is it all the same all the way through? No, not at all, right? In fact, we just got done learning about all the different layers. The crust, the mantle, the core. And the core's got iron and nickel in it, but we don't have that in the other ones, or he would have mentioned it, I'm sure. And there's this and that. And the crust is obviously different than the mantle. We wouldn't have drawn a line there. So you know it isn't. And scientists knew it wasn't. So somebody had to think back, do a little reverse engineering and say, you know what? On the first day, I bet it wasn't like this. Okay. And guess what? They got their name in a book somewhere and the biggest vocabulary word of the semester award. So the homogeneous accretion theory tells us on day one and through likely day, Lord knows how long, okay, the Earth was a mixed up, muddled up mess, uniform, if you would. However, over time, something called density separation. I used that word a couple minutes ago and said we already talked about it. I was wrong. It's right now that we talk about it. Density separation isn't that complicated either. You're actually familiar with it. Any of you have orange juice this morning? Oh, come on. Any of you ever had a glass of orange juice in your life? Okay. What do you do before you pour yourself a glass of orange juice? You shake it. Why do you shake it? All the good stuff's on the bottom and it leaves you that watery orange stuff on top, right? That is density separation. The heavier stuff settled out. You shake it back up to make it homogeneous. Ooh. All right. That's actually the amazing chemistry going on in the milk that you buy, the homogenized milk. They do something magical to it to make that fat stay in the milk instead of separating out. Anywho, so you make your orange juice every time you drink it, you make it rehomogenized, but, so this is the homework now. Next time you go into your fridge, next time somebody buys some orange juice in your house and it's sat there for a couple days, look at it. It's going to be light at the top and gradually get a little darker as you go down, and then you're going to have all that pulp at the bottom. Same thing happened in the earth, except it's a beach ball, it's not a bottle. So down is the center. So all the heavy stuff went to the center of the earth and subsequently layered, and we have the lighter stuff up at the top. That's what this is talking about. Okay? What we have now is layered. What we hadn't before was not layered. By the way, on the test, the word differentiated is here. Differentiated. I don't know why I focused on that word with the test question, but I talk about differentiated and undifferentiated. And while I encourage you guys to come up and ask questions during the test, it was just one, and it still sticks in my head. I felt so bad. Somebody came up and just couldn't process what differentiated meant, and subsequently could not process what undifferentiated or non. And they came up and asked me, and I couldn't, it was part of the vocabulary words. I couldn't, and I said, it means not differentiated. And they're like, looked at me like that really didn't help. And I said, well, look at the majority of the word. What is the majority of the word? He said, different. I said, okay, so undifferentiated is, like, not different? I said, yes. So we got there, all right? But every so often that throws you off because I don't use it when I'm talking. I don't use the words differentiated and undifferentiated for some reason. So differentiated equals layered, just so we're all on the same page here. And undifferentiated or non-differentiated equals homogeneous. All right. What do we have going on in the background here? I see some letters peeking out. Oh, Getty Images. It's the copyright. Okay. So, we've got a cool little volcanic explosion going on there. And in the background, we see some dark rock, probably in shadows, but also definitely is dark rock. That red stuff shooting up, which isn't fire, it's probably magma bubbling over, up and over lava, and all that wonderful smoke and steam. And it's a perfect picture for this conversation because this is, this is what happened next. So, remember that Earth we showed you a couple minutes ago that had a bunch of dark gray spots on it, but still some big seams, right? It was almost more seams than it was dark gray rock. Well, at some point, it closed completely up, or almost completely up. For conversational purposes, we're going to say that the crust hardened. All right? It took about 1 billion years. You see that approximately 3.5 billion years ago. We started it 4.5 approximately billion years ago. So we've been a billion years. Just in case you're making a mental timeline. The Earth cooled off, and I wrote shrank. Crust shrank. Why did the crust shrink? Well, some of you know, some of you don't know. There's an expansion and a contraction tied to heating and cooling. Okay? When things get heated up, they swell or they expand. When things cool off, they contract. All right? There's joints and bridges because of that, amongst other reasons. Metal is famous for it. So the outside of the Earth cooled off, and as such, it began to shrink a little bit, go back down to, well, probably its proper size. However, unfortunately, the inside of the Earth was still rather hot and molten, and it did not shrink. So the only way that crust could fit around the remaining Earth is for giant cracks to form. At this point, I usually have you guys bring up the image of a onion here at the grocery store and all the onion skins. As that onion continues to grow, the skin on the outside cracks because the onion inside is growing. So you get this idea of a cracked sort of shell over a whole thing. The Earth isn't growing, don't get me wrong. It's really the opposite, but it's the visual that we're going for. So you're just going to have to trust me on this one, that, no, I thought I'd have another picture, that there's a lot less cracks than this at this point, okay? Picture a couple seams like a baseball or a softball at this point. All right, just needed a couple big cracks to open up, and the crust more or less fit over the Earth. It didn't shrink that much, but it shrank enough that it broke in a couple places. Well, once that happened, guess what? The lava started leaking back out. Okay, and we use the word fissure eruptions. I think that is on here somewhere. No, we don't have the word fissure eruption on here. That's what they call it when you don't have volcanic activity coming through an actual big pointy mountain. Just a crack in the Earth opens up and Mother Earth bleeds. That's a fissure eruption. So again, picture this softball, and as it is, turns out the threading is red, so there's your lava coming out at a handful of places. Now, we haven't talked about volcanism yet, at least this semester. But in addition to the lava and the ash that you all probably know about, there's this big, thick, billowing clouds of smoke that come pouring out. And that's not your usual smoke. It's all kinds of different gases. Majority of which is water vapor, which it looks like a big steam cloud. That's because that's why. All right, tons and tons of water vapor billowing out of this thing, but with all kinds of different gases and elements embedded in it. So during this fissure eruption, during this worldwide volcanism that I said is now happening through those seams on the softball, we've got all of these gases billowing out. That occurrence is called outgassing. Okay, as the head of the slide here says. Outgassing goes on to this day whenever there's a volcano. One senator who actually did a little scientific reading pointed out one day in some of the climate hearings that more greenhouse gases come out in a volcanic event than a large city produces in a year. And, well, they may or may not have been 100% accurate on that one. An important difference they neglected to mention is that not all greenhouse gases are the same. Water vapor does indeed, tons and tons of it, billow out of a volcanic eruption. And water vapor is a greenhouse gas. But it's nowhere near comparable to carbon dioxide for its greenhousing abilities, if you would. At any rate, tons of this stuff comes out during any given eruption. No argument there. But worldwide, this is happening for a very long time. And we call this event outgassing. Out of this outgassing, out of this softball with the red seams that is billowing out lava and gases that is our Earth at this moment, we're going to tell you that the Earth gained its first atmosphere. Outgassing gave us our first air, our first atmosphere. Now, looking at this list, that's pretty foreign from what we just talked about as our current environment, right? You see the nitrogen, you see the oxygen, we have a potentially much simpler atmosphere right now. You see carbon dioxide, hydrogen gas, NH3, CH4. Who recognizes those? One of them's ammonia, one of them's methane. Which one's who? Anybody remember? All right, well, we got ammonia and methane, hydrogen gas, carbon dioxide, water vapor. That's our first atmosphere. Please note there is no free or breathable oxygen present. Some of you that are still keeping up, I've been talking pretty long and pretty heavy here. Some of you that are keeping up with me are thinking, hopefully, say, wait a minute. Didn't you say the whole Earth was this lava earlier? Why didn't we have an atmosphere then? Right? That's what you're thinking. That's a good question. Because what holds the atmosphere to the Earth? Gravity, right. That gravity's essentially been there since day one, unless gravity's somehow affected by heat, and we don't know that, and I don't know that it is. So what's different? What's different is the average surface temperature, the ambient surface temperature. Okay? When we were a flaming ball of goo, yes, these gases were seeping out all the time, but the Earth was so dang hot that they just boiled off. Okay? They were burned away. Now that the majority, remember that softball, I use that image for a reason. Okay, the majority of that softball is white, is solid rock, which is just those giant seams everywhere. Giant seams all around it. The majority of this planet is solid and cool. The ambient temperature is significantly lower. And as these gases come out this time, they don't burn away. They don't boil away. They're allowed to collect at the surface. So we do get our atmosphere, finally. Again, nothing like you've come to know and love, but over time we'll get there. Questions? Okay. I think I am going to pause. Yes, we don't want to get into weather yet. So I'm going to pause right here, and we will call that a break for the day. We'll finish up this PowerPoint finally. Oh my goodness, this is a long one. On when next we meet.